Hello, Algebra 2 folks, and welcome to the third day and final day of 6.2 Radical Operations. So today we're going to take those radicals and we're going to add them, subtract them, multiply them, and divide them. You'll need your flip chart organizer or your notes if you're not using the flip chart organizer, perfect roots chart, that yellow sheet, a calculator, and a pencil to take some good notes. All right, so let's see what we already know. We're going to have to be able to simplify today either at the end of our problem or before we start. So let's make sure that we know how to simplify. So if I want to ask you how to find the square root of 50 and I want it simplified, what would we do? Well, we would find a perfect square that goes into 50. That would be 25. How many times does the square root of 25 go into 50? Well, that would be 2. And so the square root of 25 times the square root of 2 is what the square root of 50 represents. The square root of 25 will now become 5, and the square root of 2 stays as the square root of 2. Now that's without variables. Let's recall how we do this with variables. All right, so like I told you yesterday, I would separate these two because there are two parts to it. There is the cube root of 128 and there's the cube root of x to the fourth. Those are two separate things that I need to look at differently. The cube root of 128. I'm looking for a perfect cube that goes into 128. Now remember, you need the largest perfect cube. And so the perfect cube that works is actually 64. That is the largest one, and it goes in there 2 times, and the cube root of 64 is 4, and the cube root of 2 stays the cube root of 2. Now, when we do variables, remember, we're going to rewrite it in rational, which is x to the 4/3. We're going to think backwards. We're going to be thinking about fractions that add up to be 4/3. Well, and remember, one of them is always the easy one, 3/3. Okay, and what would the other fraction that would be left over? That would be 1/3. Okay, so is 3/3 plus 1/3 4/3? Most definitely. And 3/3 turns into an x to the power of 1. And, oops, sorry about that. And x to the 1/3 stays as the cube root of x. And since I can say that's the same thing as cube root of x, I can go ahead and just add it right behind the 2, so I don't have to have 2 cube roots symbols there. Okay, and that would be my answer. All right, so what are we going to do today? Well, we're going to have to be able to simplify, but we're also going to have to be able to add, subtract, multiply, and divide. So now if you take your roots chart out here, we are going to be spending some time on this. This is our third and final day on 6.2. So if you'd open your flip chart to that third and final tab, you will notice that inside, up here, we are going to make some notes. So first we're going to talk about multiplying and dividing. And then down here, we're going to talk about what we do when we add or subtract. Okay, so we're going to take some notes on those, and then we're going to do our examples down here. Okay, so example number 1 is going to have to do with multiplying. Example number 2 is going to have to do with dividing. Example number 3 has to do with adding, and example number 4 has to do with subtracting. So this is where we are going to put our 4 examples. All right, let's get going. Let's start with multiplying and dividing. So this is problem number 1. On problem number 1, it says the cube root of 5 times the cube root of 16. Well, because they both have a cube root and a radical sign, we can go ahead and multiply those radicals. So that would be the cube root of 16 times 5, which would be, I need a calculator here, 16 times 5, or 16 times 5 would be the cube root of 80. So now what I can do is I have my handy dandy yellow sheet, And I might be able to simplify that in a better way, because obviously 5 and 16 didn't work. So what's a perfect cube that goes into 80? Well, I know one. 8. How many times does 8 go into 80? 10 times. Don't we know that the cube root of 8 is 2? And the cube root of 10 would just say the cube root of 10. So this actually simplifies into 2 cube roots of 10. Okay, what am I going to do if I divide? Well, if my index here, which is a 4 here and a 4 here, is the same, then I can go ahead and take 80 divided by 5. Well, 80 divided by 5 is the 4th root of 16. I'm going to look on my handy dandy sheet, the yellow sheet, and see if 16 is in the 4th root pile, and it is. It comes out to be 2. So the answer to that problem is 2. So my question is, and that was example number 2. My next question is, and you don't have to write this down, but I want you to think, what happens if our problems would have looked like this, where it says the cube root of 5 times the 4th root of 16? Well, because these indices is plural for index, because each index is not the same, we cannot multiply the 5 and the 16. So we would have to look at these individually. Well, what is the 4th root of 16? We just did that, didn't we? That was 2. The answer would be 2 cube roots of 5. That's how the answer would end, because I can't take 5 times 16 and get 80. Okay, what about if I had a square root of 80 over the 4th root of 5? Well, again, the index on a square root is 2. These aren't the same. So what I would have to do is individually simplify each one. Okay? So what's the rule? The rule is, if I want to multiply or divide with radicals, I can only do so if the index is the same. You cannot put the radicands together if the index is not the same. So the index has to be exactly the same. And I didn't mean to cross that out. I meant to underline it. The index has to be exactly the same. All right. So let's go ahead and do some adding and subtracting and see what happens with that. So the last two examples are going to be adding and subtracting radicals. And so here we are with problem number 3, and we are going to add these two radicals. Let's do a little sidebar here for a second. So if you were going to go ahead and add 2x plus 3y, what would that give us? 2x plus 3y, right? Because they're not like terms, we can't add them together. Can we take 2x plus x and add them together? Of course, we can get 3x here. All right, so when you look up at this problem and it says the cube root of 5 plus the cube root of 40, I'm hoping you're thinking, well, they can't really be added together because they don't even look like each other. They're kind of like the x and the y down here. So what we can do is we can simplify, maybe, and if we simplify them and we get them to look the same, then they might be like terms, and then we could add them together. So let's break down the cube root of 40. The cube root of 40 can be broken down into the cube root of 8 times the cube root of 5. The cube root of 8 is 2, and the cube root of 5 stays the cube root of 5. Well, this one is already broken down to the fullest it can be, so we're going to leave it the cube root of 5. So now when I look at this problem, to me, this looks like I have 1 cube root of 5 plus 2 cube roots of 5, which would tell me I have 3 cube roots of 5. So now that their radicands are the same and their index is the same and they're identical to each other, I can add the outside numbers. Okay, let's try it again. cube root of 2, subtract the cube root of 54. Well, to me, these don't look anything like each other. And the cube root of 2 can't be broken down any further, so I'm going to leave it the cube root of 2. But what about the cube root of 54? The cube root of 54 can be broken down into the cube root of 27 times the cube root of 2. The cube root of 27 is 3, and the cube root of 2 stays the cube root of 2. So I have the cube root of 2 subtract 3 cube roots of 2. Well, how many of them do we have of the cube root of 2's over here? We have a 1. So if I asked you what 1x minus 3x was, I would all hope you would tell me that's negative 2x. Same thing here. What's 1 cube root of 2? Subtract 3 cube roots of 2 would be negative 2 cube roots of 2. So when we add and subtract, and this was problem number 4, we have to make sure that the radicands are the same and the index. So when we add or subtract, you must have like radicals, okay, completely like radicals. So the index has to be the same and the radicand has to be the same. Okay, so the index and the radicand have to be the same. We can't have anything different, otherwise we can't add like terms. All right, that's it for now, and we'll see you back tomorrow to start practicing them. Thanks, and have a great day.